All right, today we're doing the second practice problem for homework number 4. This one is involving numerical heat transfer for 2D heat conduction. This one will be a bit long, so stick with me. Okay, to restate the problem, we're given this geometry right here, kind of a square with a square within it, and our material is actually this part right here, and it's hollow in the center. We know that this inside surface is at 600 Kelvin, and we know the thermal conductivity of our material being 1 watts per meter Kelvin. Nice and convenient. On the outside, we have convection heat transfer with T infinity of 300 Kelvin and a convection coefficient of 50 watts per meter squared Kelvin. All right, we are asked to find the temperature at certain points. But before we do that, we're going to break up this problem. It's intimidating to try and turn this whole thing into a numerical mesh, but luckily we have symmetry. If you split this thing down the middle, the temperature profile on the left will look like the temperature profile on the right. Likewise, if we look diagonally in this direction or this direction, the inverse of each other, the temperature profiles will look the same. So what that means is we only need to look at this chunk, because here is where we can find the temperature variation. And the temperature profile here will look like the temperature profile here, and the temperature profile here, and the temperature profile here, and going all the way around. So what I've done is I've taken this triangular piece and I've put it here for you, made it larger, and labeled some nodes, some temperature nodes. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I've drawn these lines. These are symmetry adiabats, which is a cool sounding name. Really the only thing it means is that there is no heat transfer going directly across because, again, of symmetry. The temperature profile coming up to this point looks exactly like the temperature profile coming up to this point, which means we will have a gradient of 0 going along this line. Okay, we're going to use that in the future, but for now let's define a few key terms, what we know, and then we will solve it. So we're going to define a distance delta x, being the distance between any node in the x direction, and delta y, the distance between any node in the y direction. We're going to set those equal and let them be equal to 0.01 meters. Okay, we know a few temperatures. We know the temperature of our first node is 430. We know the temperature of our third node is 394 Kelvin. We know the temperatures of nodes 8 and 9 at the bottom, right, because those are touching this surface. They are this surface, which is already defined as being at 600 Kelvin. And finally, we know the temperature at node 6, which is 492 Kelvin. Okay, before we wrap up here and solve the problem, let's just list what we need to find. The first thing we need to find are equations for nodes 2, 4, and 7. So equations that would allow us to calculate the temperature. We also need to find the temperatures for 2, 4, and 7. And finally, the total heat rate due to convection from this surface right here. So how much is leaving per unit depth into the board? That's what this Q single prime means, is the amount of heat transfer from this line per unit depth due to convection. So it's the heat is conducting through this material, reaching the end, and then convecting into the air. Okay, let's approach this problem. Okay, now that we've set up the problem, let's approach the 3 different nodes using a balance, a control volume in each node, and solve for it. You can use a different color marker so we can keep track of what we know and what we're doing. Okay, so first we're going to do node number 2. That is this node right here. I'm just going to draw our control volume and then bring it over here to make it larger. So here is node number 2. Bordering node 2 on the left is node 1, and on the right is node 3. Below it is 6. So what we do is we draw a control volume that is halfway between each node. And since we're on a surface, we just draw that control volume, including the surface, and not going anywhere above it. So defining some lengths, this distance would be delta x over 2. This distance would be delta y over 2. Okay, let's define some heat transfer terms. Coming in from the top, we'll call QA prime. From the right, we will call QB prime. From the bottom, QC prime, and from the right, QD prime. Remember, we just define all heat transfers coming in. Obviously, that's not how it is, but the signs will work out as we do the math. So what we do is we do an energy balance of our control volume. In other words, we're going to say that all of these heat transfers coming in, added together, must be equal to 0 because energy is conserved. So now what we have to do is redefine each of these in terms of variables like delta y and temperatures of nodes. And we'll be able to solve for the temperature of the node. So we'll start with QA prime. QA prime is convection heat transfer from T infinity into 2. So we're going to start with the basis of Newton's law of cooling, which we begin with the convection heat transfer coefficient multiplied by the area over which this convection is occurring. This convection is happening at this interface, so we use this length, delta x. Remember, this is all per unit depth into the board. Then we always say the heat transfer goes from in the direction of the arrow, so T infinity to T2. So T infinity minus T2. That's QA. Let's try QB and see what we get. QB now is this right term, it's conduction from 3 to 2. So we start with the basic Fourier's law of heat conduction, or thermal conductivity. Now we multiply by the area conduction is occurring through, which is delta y divided by 2. Delta y is the vertical distance between nodes. Our control volume is half that distance. Then we multiply by the difference in temperature, again, hot to cold, or in the direction of heat transfer, T3 to T2. And we need to divide by the distance. Remember, Fourier's law has a dt, dx. So this is our dt. Now we need a dx, which would be the distance between 3 and 2, or delta x. Okay, we need to do QC. QC looks a lot like QB. So we begin with K. But now, instead of passing through half of a surface, you see our conduction is over a full surface, or delta x divided by 2 times 2, or delta x. Again, we go from in the temperature difference in the direction of heat transfer, so T6 minus T2, divided by the distance between nodes, which in this case would be delta y. Okay, finally, we need to do QD. QD looks just like QB. And so it actually ends up being an equivalent statement aside from the temperature terms. Now, we need to go in the direction of heat transfer, so 1 to 2. T1 to T2 over delta x. Okay, so we have solved for all 4 of our heat transfer terms in terms of things like H, X, and temperatures. We plug all of these in here, solve for T2, plug in what we know, and we can get what T2 is. I'll go here at the bottom where you can still see it. I'm not going to do any of that here, but the final answer is 422 Kelvin. Okay, moving on, we're also supposed to do node number 4 right here. We're going to draw our control volume halfway to node 3, and then we're going to take in parallel to our adiabat. So let's zoom in on that. I'll just draw a little line here so I can keep track of where I am. Okay, so here's node 4. Here's node 3. Here's our symmetry condition. And here is our control volume. All right, so like here we draw the heat transfer terms we have. In this case, from the top, we have QA prime. And then coming in across the symmetry adiabat, we'll define a QB prime. And then coming in from here, QC prime. Again, we add them all up. We're just doing an energy balance of our control volume, and we solve for each in terms of temperature, convection coefficient, distance. So we'll start with QA prime, which is the convection coefficient. Again, just like here where we had QA, we start with H. Now multiply by the area or the length that convection is occurring over. Remember, delta X is the distance between nodes. Our control volume is half that distance, so it's delta X over 2. Okay, then we multiply by the difference in temperatures following the direction of heat transfer we've selected, T infinity minus T4. QB prime is just equal to 0. Remember, this is crossing a symmetry adiabat, which by definition is a place where heat transfer is not crossing, as long as that heat transfer is perpendicular to the line of the symmetry. Okay. Finally, QC prime is conduction from node 3, and that we're going to use Fourier's law again. We haven't drawn it here, but the next node would be down here. We've drawn this as delta y of 2 is our distance there. And again, we need to account for temperatures. We go in the direction of the arrow, T3 minus T4, and we divide by the distance between them, delta x. Okay, if we add all of these up, again, put everything into this equation, solve for what we want to know, which is T4, then we can get what T4 is as a function of all these other parameters. We should get that equation, box it, and then solve that equation for temperature. Then what you get is 363 Kelvin. Okay, finally we're asked to do node number 7. Node 7. Okay, node 7 is right here. We're actually just going to talk about this one right here. So a symmetry adiabat, we can reflect this across, which means that we have over here a node that is equivalent to 3, and down here a node that is equivalent to 6. This has been rotated downwards. So 3 and 6 ended up here. Now you recognize that we just have conduction into each side from nodes that are equally distant from our central node. This is an interior node. So look up an interior node in table 4.2, interior node. And then we look up the equation, and all we're going to get is T3 plus T3 plus T6 plus T6 plus 4 times T7 equals 0. Okay, now it just remains to solve for T7, which is easy with this equation, and we get 443 Kelvin. Okay, we are almost done with this problem. We have one more part to do, so stick with me. Okay, the last part of our problem, which we will do in pink, is find the amount of heat transfer per unit length due to convection leaving our surface. Again, we have heat conduction moving through here, hitting the surface, and then being convected away. So to do that, we're just going to redraw the topmost surface with our nodes 1, 2, 3, and 4. And then we're just going to draw control volume like this. And we are going to try and find the total amount of convection. In other words, the added contribution of each node. So we're just going to call this Q1 prime, Q2 prime, Q3 prime, and Q4 prime. Okay, where the total heat transfer from the control volume is just equal to the addition of all 3 of these heat transfer terms. Okay, let's define each one. So Q1, looking here, is just equal to, again for convection, we start with H, Newton's law of cooling, multiplied by the length. Now this is starting at this node, and we're going to go halfway to the other node. So our specific length here is delta x divided by 2. Okay, multiplied by our delta T in the direction of heat transfer. So T1 minus T infinity, or the temperature of the air. Let's do Q3, which is equal to, again, we start with H, and then multiply by the distance. Let's draw our control volume for 2. Since this is interior, 2, 1, and 3, we draw our control volume halfway to each node, which means the total length is delta X. So delta X, again, times our delta T, which in this case is T2 minus T infinity. Well, Q3 is the exact same story as Q2, so we're just going to write that out. Now we use the temperature of node 3, T3. And finally, Q4, which would have this control volume, is the same story as node number 1, where we do H, and now we have to only do half of the length, since we're only looking at this length right here. And then we multiply that again by our temperature difference. So we can just put all 4 of these equations together and add them up. We know H, delta X, and we know all of our temperatures now that we have solved for T4. And we can solve for the total convective loss from our surface, which is going to be equal to 156 watts per meter. Okay, as a discussion, let's remember that this is only for the piece we looked at. This section right here, remember our entire scenario looks like this, and we've only modeled the convection right there. So if we really want to know the total heat loss, we'll need to multiply by all of the sections. All right, that was our lengthy but instructive numerical heat transfer problem. Thanks for watching.